All right, so we have this example here where someone has applied the brakes and we want to find out how far they've gone given that we know the velocity of the car at 0 to 4 and 6 seconds, right? Our velocity was 88 feet per second when they first applied the brakes, 45 feet per second after 2 seconds, so on and so forth, right? And so we want to find the total distance, right? And what we're going to do is we're actually going to use that rectangle area under the curve rectangle type of situation to help us do that. Now, I don't have a curve here, all right? Now, but if I wanted to estimate a curve that represents the situation, then I can just plot this stuff in on this graph here, right? So at 0, we had 88 seconds, for instance. So we have 0, 88. This is going to be an approximation. 245. 245. I almost put that as 145. 416. And 60. That's when the car comes to a stop, right? And I can try to draw a curve that represents that rate of change, okay? Something like that. Now, if I wanted to provide lower estimates of the velocity or the total change, right? Of the total distance traveled, right? Lower estimate means use rectangles that underestimate the area under the curve, and upper means overestimate the area under the curve, right? So lower means underestimate, and upper means overestimate. And I'm going to use rectangles because I want to find the distance traveled and I have my rate of change here, right? And so if I think, right, I have these intervals from 0 to 2, 2 to 4, and then 4 to 6, right? And so if I'm going to find an underestimate for the area under the curve from 0 to 2 seconds after the brakes applied, right? Then what I'm going to do is I'm going to choose either this endpoint on this interval, which is at 0, at t equals 0, or I'm going to choose this endpoint, which is at t equals 2. And if I want to underestimate, I've got to use this endpoint here, right? And this is going to be my first rectangle that I'm going to use in order to help me get the area under the curve. And this is going to give me an underestimate, right? All right, from 2 to 4 seconds, I got to use the smallest y value, the smallest y value, and I'm at the opportunity to use this one here. I don't know why I said opportunity, but it's this one here. And then last but not least, from 4 to 6 seconds, the smallest y value is 0 here. It's not really anything. But as you can see, if I do the area under the curves, these rectangles here, it's going to be an underestimate because I have this space that's left that I'm not taking care of, right? The other option is for me to use an overestimate. Overestimate means to upper estimate means to give an overestimate, sorry. That means I'll go to each interval from 0 to 2, 2 to 4, 4 to 6, and I'm going to choose the endpoint that has the highest y value. For instance, from 0 to 2, this one's bigger. So my overestimate is going to give me the rectangle that I get here, and I find the area of that rectangle. From 2 to 4, I'm going to use the rectangle at 2. And I calculate all of this area. And then from 4 to 6, I'm going to use this endpoint. It's going to give me a higher rectangle that overestimates the area under the curve. And it's an overestimate because I have all of this extra stuff that's actually above the actual area under the curve that I'm interested in, right? And so what I'm basically trying to say is that there are multiple ways that we can estimate these area of curves, given that we're going to be using rectangles. So if you go and each interval you use the smallest y value, you're going to get a lower estimate, and if at each interval you choose the highest y value, then you're going to get an overestimate, okay? So this is doing lower and upper estimates. Let's actually calculate these things now that we visually know what they are. And so I'm going to give the lower and upper estimates for these in this here, right? So let's go to lower estimate. Okay. All right, the lower estimate, we're going to do the area of the curve, which is the area of the rectangles. And so what I'm going to do here is I'm going to go and I'll look at my interval from 0 to 2. It has a width of 2 units. 0 to 2 is 2 units, right? So it's going to be 2. And since I want a lower estimate, I use the y value that's the smaller or the minimum on that interval, which is 45. I'm going to go from 2 to 4 seconds, right? The width of that rectangle would be 2 units, and the length would be, well, choose the smaller one. It would be 16. And then for my interval from 4 to 6, that has a width of 2 units. And the height will be the minimum of those, which will be 0. Okay? We're going to start writing it like this. So that's why it's just 2 times 45 plus 16 plus 0, which we can write as 122. And since this is in seconds and this is in feet per second, when I multiply them, the seconds cancel and then I'm left with feet. Okay? And so that's 122 feet. Let's find our upper estimate for the distance traveled after they apply that brake. And so I'm going to basically do the same thing, but on all of my intervals, I'm going to pick the maximum y value on that interval, right? So from 0 to 2, my width would be 2 for that rectangle, and the maximum from 0 to 2 is 88, so I get 2 times 88. From 2 to 4, I have a width of 2, and my maximum height will be 45, so I get 2 times 45. And then from 4 to 6 seconds, that's 2 seconds, and then my maximum on that interval is 16. And I say maximum height. It's the maximum height on the graph, but it's actually the maximum velocity because these actual numbers represent velocity. So I do want to make sure I clear that up. It's not a height. But I could write this as 2 times 88 plus 45 plus 16 since my intervals are equal. You don't have to do that. I'm just doing that because you may see it later. And this will be 298 feet when I calculate these things here. Okay? So this is how we calculate the area under the curve, and this is the using lower and upper estimates by looking at rectangles, okay? An alternative to looking at upper and lower estimates is to look at what we call left hand and right hand sums, all right? Now, I have a function here. So in the last example, we had a table. And now I have a function, f of t equals 3 times t minus 5 squared. This represents the rate of change of some quantity, right? Since that represents a rate of change, then we're going to estimate the total change from t equals 0 to t equals 4 using 4 rectangles by using left-hand sums and right-hand sums. And so this gives us an alternative way of actually calculating the area under the curve, or to calculate or estimate the total change. So in the previous example, we looked at upper and lower estimates, where we go to each interval and choose the minimum rate of change when we're talking about lower estimates, and we choose the max rate of change when we're talking about the upper estimates. Left hand and right hand sums can actually equal the lower and upper estimates for some functions, but it's not always the case. And actually, this is the method that is most used to estimate total change. All right, we're going to start this example in the next. Actually, I think I have time to put in this video. What I want to do first is talk about what I mean by left and right hand sums, right? I'm going to tell you right now that the graph of this function, if you were to graph it in your calculator, it would look something like from 0 to 4. It would be a curve that would look something like this, right? When I say I'm going to use 4 rectangles that means I'm going to have 4 rectangles, right? That's duh, right? But when I say left and right hand sums, what I mean is I'm going to use the left endpoints to create my rectangles. And when I say my right hand sum, I'm going to use right endpoints, right? When I have this 0 to 4, in order for me to use left hand sums, what I'm going to do is I'm actually going to choose the leftmost endpoint and create my 4 rectangles on that interval using only the left endpoints. For instance, from 0 to 1, that's going to be one rectangle. From 1 to 2, that's going to be one rectangle. 2 to 3, that's going to be one rectangle. And 3 to 4, that's going to be one rectangle. I'm going to use the left endpoint to create my rectangles where I'm going to do my area under my curve. Okay? What that basically means is that I'm going to leave off the rightmost endpoint. My rightmost endpoint is this endpoint right here. That is not a height of any of these rectangles that I'm using to estimate my area under the curve, right? When I say right endpoint, that means I'm gonna leave off my leftmost endpoint and I'm gonna create my rectangles, okay? And so my rectangle from 0 to 4 is not gonna use 0 as the height. It's gonna actually use 1. And so let's use a different color here. My right endpoint is gonna leave off the leftmost x value or t value here. My axis is t to create the rectangles. And then I'm gonna go here. So you leave off the leftmost endpoint to get your height of your rectangle, which represents your velocity, your rate of change. And then you use your right endpoint. So here I'm using my right endpoint, and I'm leaving off my left endpoint, which would be this point here when I do right-hand sums. And when I do left-hand sums, I use my leftmost endpoint, which is that one there, and I leave off. So I use this one, this one, this one, and this one, but I leave off this last one, which would be my right. And so it's not a height of one of those gray triangles, right? And so this is basically the difference between using a left hand and right hand versus using a upper limit and a lower upper estimate and a lower estimate. We're going to actually do these in the next video.